All right, so today we're going to be doing day 9 in Advent of Code, disk fragmenter. So what we have to solve is that we get a long list of numbers, and each number represents a different thing. So the first number represents how many spaces of data there is, and then the not following number is going to be how many spaces of empty data there is. And we see some examples here. If we get 1, 2, 3, 4, 5, there will be a 1 block file followed by 2 empty spaces, 3 block file followed by 4 empty spaces, and then a 5 block file. And in this example, we would get 3 9 block files with 0 spaces in between them. So this is how it would look like if we got the 1, 2, 3, 4, and 5. And the reason that it says zeros, ones, and twos is because they each have IDs. So the ID begins at 0, and then it keeps incrementing by 1 every time. So if we have this example over here, then this is the result that we get. So we see that the first 2 means that the first disk size is 2. So the disk size with the ID 0 is going to be too large. The next number is a 3, so there's 3 empty slots. Next number is a 3 again, so there's 3 disk size with the ID of 1, and so on and so forth. And what we're trying to do is to compact the disk. So we will take the last digit that we see and we put it in the first empty space that we see. And we see that we took the 9 from the last space and we put it in the beginning. And we keep doing that, keep doing that, keep doing that until there's no empty spaces left. The empty spaces should just be at the end. And then we want to do a checksum. So we take the index, I believe. Yeah, and then we multiply it by whatever number is here, whatever ID is here. And then we sum those, and that should be the result for this problem. So the solution, I've opened the file, which I've put it in input.txt, and it's a really long file, and it's just 1 line. And then what we can do is to just put everything in disk map, and I want to get all the disk segments separated. So every other number is, well, the first one is going to be a disk segment, and then how many empty spaces, disk empty, disk empty, disk empty, and so on and so forth. So I will call them file length and free length, and I will iterate through it. And if you say for I in range, you can say the beginning of the range, the end of the range, and by how much you want to step. So we will begin at 0, we will end at the length of the map, and I want to step by 2 every time that I do this. And this way we can get the file length and the free length, and we can append to the disk segments either the word file or the word free, and then the file length or the free length. So if I debug this real quick, and we just look at the disk segments and how they look, we can see how it's going to look in the memory. So disk segments, it's going to look like, okay, file 9, free 2, file 4, free 3. So if we look at the input, we see that we get a 9 at the beginning, which is a file. We get a 2, which is free. We get a 4, which is file. We get a 3, which is free, and so on and so forth for a lot of different lines. So it's always going to be free file, free file, free file. Then the next thing that we do is that we build a disk representation, and we have it here as well in memory, I believe. Disk representation. And we have it in blocks. So if we look at the blocks, we can see that, okay, the first one was number 9, so we will have 9 zeros followed by 2 empty spaces because the next number was a 2. And the zeros are the index of the disk, so it will be 0, 1, 2, 3, 4, and it will keep going, and it will even get to double digits, but that's not a problem because we're storing it together, so it's not going to be a problem for us. So then we have for each segment and length and the disk segments, then we want to check if it is a file. If it is, then we just want to add it and multiply it by the length, so it's going to appear several times. Otherwise, we just put nothing in here, like we can see. And then the step that actually solves the problem is to compact the disk. And the way that they want us to do it is to look at the last digit. So we have to look at the last digit here, and we have to find the first empty one and put it over there. So that's what we're going to do. So we're going to make a left walker and a right walker, which will keep track of the first position where it's empty and where we can put a letter or a number, and then the last place where there is a number that we can take from. So while the left walker is less than the right walker, because we don't want them to cross each other, that means that, okay, we've already iterated through everything and we can't really swap anything else. Then we want to check that the left walker is less than the length of the block, so that it is not out of bounds, and that whatever is at this index is not equal to a dot. Then that means that we've found a number. And then the other walker, the right walker, should find a dot, so it should find an empty place, and then what we do is we swap them here. So this is what this line does. So once we've compacted the disk and we've swapped a bunch of different variables with each other, we calculate the checksum. And if I can just run it until this stop point here, it's going to stop here, and the blocks is going to update. So we're going to see how it's going to look actually. So here we have blocks. It used to be 0000 something, and then nothing in here. But now we see we have block 9999 and 9998, which is presumably the last blocks. And we can see the last block is only one long. So that's correct, that there's only one 9999. And then the 9998 should be 3 long. Sorry, that's the 3 empty spaces. The 9998 should be 7 long. So we have 1 9998, 2, 3, 4, 5, 6, and 7, and then we continue with one less index, and so on and so on. So what this means is, okay, this file has 10,000 or 9,999 plus 1, so 10,000 different disk spaces, and then 10,000 different empty spaces. And it looks like it's correct. So if we let it calculate the checksum, which it does by just iterating through everything and then multiplying it by whatever number is here and its current index. So if I let this run to completion, it's slower when we're debugging it, but we get this answer, which ends with 4968. And let's see if it's the same answer that we got, 4968. So that was part 1. And now for part 2, what we have to do differently is that apparently they noticed that this is very, very slow. What we want to do is when we find a disk, we take all of its IDs, and depending on how big the disk size is. So this disk with ID 9 is of size 2 because there's 2 9s, and we have to move the entire thing into an empty space somewhere that we can find. In this case, it fits here. Then we check for the 8s. The 8s don't fit anywhere. There are 4 of them, and they don't fit in these 3. They don't fit in these 3 empty spaces. So actually, we don't do anything. Now we check for the 7s, and the 7s do fit in here, which is great. Then we check the 6s. They don't fit anywhere. We check the 5s. They don't fit anywhere. We check the 4s, and then we see that the 4s can fit in here. Then we check the 3s. The 3s can't fit anywhere because we still see that there's some empty spaces. But the 2 over here fits in this tiny space. So what we have to do is we iterate from the right. We take the numbers and we put them at the leftmost space. And we always have to check the leftmost space. We can't just say, okay, we filled this one with a certain number from the right, so we just keep checking from here. Because we can see that, okay, we filled this space here, but then we went backwards and we filled the 2 once we got to that number. So we have to iterate all the way through it again. And this will be a lot less efficient, but that's how we have to solve it. So we do the same thing. We open the file, we parse the disk into different segments, so the free and the file. We built the initial disk representation, and I'm going to have an extra thing, which is file positions, because I want to know the position, the length, and the file ID of a certain file. Then we're going to aggregate the free spaces into a list of tuples, and this is just to make it easier for us later, so that we know where all the free spaces are. Then we can move the files to the leftmost valid space. So we will keep track of a file count and a space count, and we will iterate through the file index by saying range And from the file count, so however big it is, -1, we iterate from that amount until -1. And how do we do that? We iterate through it by doing -1 every time. So it goes all the way from the file count until it reaches -1. Then we iterate again, but we iterate through the free spaces normally, so from left to right. And we always have to start all the way from the beginning in case there is a really tiny space that we've missed. Then what we do is that we move the file. So we say, okay, block start position plus j is equal to nothing. So we remove the old one and then we add the new one. Then we update the free space so that we can use this next time that we iterate through here. And this just saves some time. We could not use the free spaces, but then we will have to iterate a bit more through everything. Then we can calculate the checksum, and it's similar to what we've done here, but now it's not just with dots. I check if the block is not none instead. Then we print the checksum, and this one actually takes a couple seconds to run. And while it's running, I can talk about the time complexity of part 1. So the time complexity, building it, compacting the process and doing checksum is all O of n, which is pretty nice. And then space complexity is also O of n. So that is pretty good for the first part of this challenge. And for the second part, the time complexity for part 2 is a bit worse, since we have to iterate through 2 for loops. So we have to go at the end, and then every time that we go one step in, we have to check this entire thing. One step in, check this entire thing. One step in, check this entire thing. And so on and so on. So it will iterate n squared times in the worst case. So the total time complexity is n squared, which is pretty bad. But it's not really possible to make it better than this. Maybe a little bit faster, but you still have to check all the different iterations. And then the space complexity still remains the same, since we're not storing any more information than we were before. And the file ran. It took maybe 20 seconds or something. It ends with a 2766. So that is the same answer that we got here. So that was part 1, part 2, and their space complexities. Now, if you guys want to join the leaderboard, I will leave the private leaderboard code in the description. And yeah, thank you for watching. Happy holidays, and see you tomorrow.